Welcome back to NE 630, nuclear reactor theory. So last time we discussed the solution of the diffusion equation in several geometries, and we went through the solution in plane geometry, in plane source and infinite geometry, a line source and infinite geometry, and a point source and infinite geometry. Then we solved the three cases, but for finite geometries. So today we will discuss what we call the diffusion kernel, and it is a good technique. It will enable you guys of solving the diffusion equation, let's say in a situation where you have certain distribution of sources inside an infinite or a finite medium. So let's go ahead and define the infinite medium diffusion kernel. So if you remember for the last cases, three cases, the plane source, the point source, the line source, all those, we took the source at the center point. We said that the axis is at 0 and it is an infinite medium. So we can also move the source from the center and make it, instead of at x equal to 0, x equal to negative x instead. So let's assume that this is the plane situation, and this is x equal to 0 here. Then we make a axis transformation so that we will have our source at x equal to x prime. Of course, you're still emitting again S naught, where S naught is the number of neutrons per centimeter square per second. And then we are interested in knowing the flux at a point x. So if you remember the flux, but now our source, let's assume that our source is 1 neutron per centimeter square per second. So the flux as a function of x, if you remember last time, but now the flux is at x because of a source at x prime. Last time we used to write it only phi of x. Yes, because it's the flux of x and we know that the source was at x equal to 0. Now because we shifted the source at x equal to x prime here, so we will say the flux at point x here, because of a source presence at point x prime, it will be equal to L over 2D multiplied by e to the power of minus. Last time it was the amplitude value of x, but now x was the distance between the source and the point. Now what's the difference now? It will be x minus the amplitude value of x minus x prime. And the only difference between this case and the last time case, when we derive the equation for a plane source, that we have S naught here. But because we are using what? S naught equal to 1, so this will be what? 1 multiplied by this and x minus x prime. So this is what we call the plane source infinite medium plane source kernel. So infinite medium plane source kernel. We will see in a minute why the kernel is useful. Again, for a line source, same. We have the line was situated at, last time, was situated at r equal to 0. Now we will put our line source at r equal to r prime, and we want to calculate our flux at r equal to r. So the source now is at r prime, and the point of measurement at r. So again, for the flux, because of a line source located at r prime, and the flux is at r is equal to, what do you think? The flux in a cylindrical geometry last time when we derived it? It was k naught, the Bessel function, and now the absolute value of r minus r prime divided by L, all divided by 2 by d. And for a point, if the point last time, the 0 here, and we have the flux at a point r, so what we will do now is the source now is at r prime, and we want to get the neutron flux at point r. So this is a point in an infinite source, so this is the flux for a point source, again, of a source, unit source at r prime, and we are measuring the flux at r, is just equal to e to the power of minus r minus r prime, all divided by L, divided by 4 by r minus r prime d. So now, this is just, so if we have a spherical source, spherical shell, so it will go to infinity, so this is a spherical shell, and the other one, if we have this cylindrical shell, sorry, and if we have spherical shell, this is the case, cylindrical shell and spherical shell. So phi for the cylindrical shell at r, because of a source, unit source at r prime, so this is the shell, this is r prime, and r, let's say r is like here, and this is again r prime, and maybe r is here. So for cylindrical shell, it will be equal to 1 over 2 by d multiplied by k naught of r over k I naught of r prime over L. I think this is L. And this one is equal to k naught r prime over L I naught I prime over L. This case where r is greater than r prime inside the cylindrical shell, and this case where r, this is outside the cylindrical shell, and this is inside the cylindrical shell. For the spherical shell, the flux for the spherical shell at r as a unit source present at r prime equal to L over 8 by r prime d e to the power of minus r minus r prime divided by L minus e to the power of r plus r prime divided by L. So why we are doing all this stuff here? So those are Stacy put all those in one page. So why we bother knowing this kernel, for example? Because this is just the flux because of a unit source at x prime or r prime. If I have now a distribution of sources, let's assume that for the plane geometry, I have 0 is here, and this is my unit source at x equal to x prime. So I knew what is the flux. Yes? If I have now certain distribution, something like this, of distribution of what? Distribution of the source. So this is the source as a function of x. It has this distribution. So in principle, what I can do is I can chop this source to infinitely many plane sources. So I will have infinitely many plane sources like this. And then I can use what? I can use the kernel to calculate the flux because of this source distribution. And it will be what? So it will be phi as a function of x is just equal to the source as a function of x multiplied by the kernel, which is the flux at point x because of a unit source at point x prime dx, and x will go from negative infinity to plus infinity. Okay, guys. So if you will notice that this is, if it is s of x, and this one will be just L over 2d e to the power of minus x prime over L dx prime from negative infinity to plus infinity. If it is point source like here, all what you will be doing is what? Flux at point R. So you will assume that the kernel is the flux at this point because of a unit source at this point. So you will assume that you have infinite unit sources everywhere, let's say with certain distribution and source strengths, let's say. So all what you will do is you will integrate your S naught of R, phi of R, R prime, dr prime. And now, where do you think the limits of the integration will be? Zero to infinity, because you are integrating from the origin to infinite everywhere. So let's see how we will calculate, let's say, a finite slab diffusion kernel. If we have a finite slab, how we calculate the diffusion kernel? Finite slab diffusion kernel. So if we have a finite slab, and this slab has borders negative a plus a, 0 here, then you have lambda extrapolated here, negative, and lambda extrapolated here. Then your source is at x prime, and let's say that it has something like imaginary thickness here. So it will be x prime plus epsilon. This is x prime plus epsilon, and this is x prime minus epsilon. So here x is less than x prime, and in this area x is larger than x prime. And you have the diffusion equation Laplace square phi minus 1 over L square phi equal to 0. And x will go from negative a to plus a. So this equation is valid from x greater than negative a and x less than a, with the exception of what? This equation is true everywhere with the exception of what? X prime. X equal to x prime. Why? Because at x prime, this is not 0, this is delta of x minus x prime. Yes? Because the source is at x prime. So at x prime, you cannot say that this equation is valid. If you want the equation to be valid, it will be S naught delta of x minus x prime. This is the valid equation everywhere. And because this is delta function at x equal to x prime is S naught, and everywhere is 0. Yeah, so this is the exact equation. But usually we write it as homogeneous equation so that we will be able to solve it. And we said that this equation is valid inside this domain except at x equal to x prime, as we stated clearly several times. So what's the flux at x prime plus epsilon? The flux should be equal to the flux at x prime minus epsilon. This is the continuity of the flux around the source. Yes, the flux around the source is the same. What about the current? The current at x prime plus epsilon equal to the current at x prime minus epsilon. Is there anything missing? The current is a directional quantity. Flux is everywhere. So the flux, this is the source, the flux here is the flux here. Just a very small infinitesimal distance from the center line of the source. The flux is the same as very infinitesimal epsilon before the source. But the current is not the same. Huh? So the current after here is the current before here plus what the source emit. Yes? In this direction. Which will be what? 1. Because this is unit source. Now, we have also the flux at A equal to what? X equal to A equal to what? 0. And this is equal to the flux at x equal to negative a. Here I did not take the extrapolated distance in place. If I will put the extrapolated distance, this should be what? A tilde. I will not use the extrapolated distance here. I will say that the extrapolated distance is very small, can be neglected with respect to the dimension A. So when you solve this equation, you will have two domains to solve this equation in. Where are the two domains? The one just x greater than x prime, and the one x less than x prime. Yes, Mohammed?
I'm just confused about x prime plus e plus epsilon. How is it equal to the j on the other side plus 1?
Because
neutrons are
if you remember last time when we deduced the diffusion equation, I stated clearly that at the interface, if the interface does not have any sources, and this is medium 1 and this is medium 2, so the flux, let's say this is x equal to 0. So the flux at 0 plus 0 plus mean starting from here, is equal to the flux at 0 minus, the flux here. And also the current at 0 plus should be equal to the current at 0 minus. But this is if we do not have any sources at the interface between the two boundaries. If we have sources, this means that there is emission of neutron from the source in both directions. So the flux will be the same because the flux is the total number of neutrons going everywhere. But because you are talking about directionality now, what current is here, the current means the number of neutrons moving per centimeter square in this direction. So current, this is without source. Without source. Now, if we talk about J0 minus, plus, sorry, the current here at this location, which is total number of neutrons per centimeter square moving in this direction here in this medium. So the neutrons that will be moving from this medium up to the interface will then collect the number of neutrons generated in the source in the interface and move all together to the other medium. So it will be J minus, whatever you have it here, J0 minus, will move in, will collect the source term, half of the source term. Let's say that this emits S naught over 2 in this direction and S naught over 2 in this direction. So it will emit half the neutrons and move this direction. Some of the books will write it one fold. So this source is unit source, so we write it 1. Okay? So now, to solve this equation, you have to solve it for two cases, for phi plus and phi minus, and plus means you are on the side greater than the source, and the other minus means you are in the side where you are less than the source. And this will give you phi plus at x, because of a source at x prime, will be equal to sinh the hyperbolic sign of a plus x prime divided by L multiplied by sinh of a minus x over L divided by d over L sinh of 2a over L. And this is phi minus of x as another unit source at x prime is equal to sinh of a minus x divided by L sine sinh a plus x over L all divided by d over L sinh of 2a over L. This is phi minus. I don't know if I forgot to put a prime here. Do any of you have prime here? Did you have the book with you?
Yeah.
Okay, so thank you. Can I get your pen so that I will put it here? And then if you want to get those are the kernels now for this medium. If you want to get the flux will be the integration from negative a up to the point x. Let's assume that the point x is here. Let's assume. Or the point x will be here. So you will integrate from negative a to the point x, where x is less than x prime. So you will use the formula for the flux in this area. Then you will integrate from x equal to x prime to a, and you will use the other formula, this one. So now this will give you the source at x prime, phi plus at x dx prime plus the source at x prime p of x at x prime dx prime. I think from x to a, something like this. You have to. Did you see the limits?
Yeah.
What's the limits for? Can I see the book?
Yeah, negative a to x and then x to a. Yeah, you get the right one.
So this is negative a to x for this one, and this is x to a, and this is phi minus, and this is right. Okay, so I got it right. Oh, sorry, I'm sorry. I'm sorry. Can I get the pen again? Sorry. So this is x to a.
Is the second one phi minus
Which one?
on your second integral?
Yeah, phi minus. Thank you.
Why is this one phi minus when you're in the upper x values?
Where?
You're going from x to a, so that's
Yeah.
to the right.
Here. Yes.
Is that phi plus or is that phi minus?
No, minus. Minus why? Because if your point is here, this is x and this is x minus. So your source is less than the point that you are measuring at. So this is phi minus. And phi plus is where the point x is here and the source is here. So the source is at a positive location with the measuring point. So minus and plus are with respect to where is the source located with the measuring point. Okay? So phi minus and phi plus is where is the source with respect to the measuring point. So let's look for the case where we have a slab like this, and now it's a finite slab, but we have incident neutron beam. So there is neutrons that are incident to the slab from the left-hand side. So this is J. And this, we will not call it J, I will call it S. S naught of X. And the definition for S naught of X, this source has this form. Q naught sigma scattering e to the power of minus sigma total of X plus A. Okay, X is the location. A is the width of the slab. Sigma scattering is the scattering cross section. Q naught is the first thing here that need to be defined. You did not take it before, and this is called the slowing down density. And we will be discussing what we mean by slowing down density in I think the next chapter. What do we mean by slowing down density? You remember that the neutrons are generated up here, at let's say from the fission. Yes? So I can put a datum like this and I say all the neutrons, let's say this is the maximum energy of the neutrons that come from the fission. Those neutrons will be slowing down. So they will make a collision here, they will reduce the energy, they will get up to this level, this level, this level, this level, until they get to zero energy. And zero energy is in the thermal energy range. So if you pick any energy here and you said this energy is E, and you said how many neutrons are slowing down below this energy E from the above energies per centimeter cube per second. This is the slowing down density. So it is What's the definition now? Total number of what? Neutrons slowing down past energy E per centimeter cube per second. Okay, guys? Okay, but this is if I said Q of A. If I said what? Q of A. If I integrate this and there is no absorption and there is no leakage. So if you integrate this, this should give you what? All the neutrons that slow down per centimeter cube per second. Yes? Usually this will be related to the source function. And this is why we have it here, multiplied by sigma scattering, and it's related to the source function. If you do not have absorption or leakage. Okay, guys?
So we would integrate Q of E over all possible energies?
If you want to get not as a function of energy, you have to integrate over all energies. This will give you total slowing down density, and this means that those are the total number of neutrons slowing down. If they slow down from energy E and there is no absorption and leakage, they will reach to zero safely, because there is no absorption, there is no leakage. If there is any shark in between, part of them will reach.
Is that what Q naught is in our essence?
Yeah. Q naught is the slowing down density, total slowing down density, total number of neutrons slowing down. Okay, but here Q naught is energy E naught, let's say. So it's not, Q naught is at energy E naught. So it's not the total. Those are number of neutrons below S naught. And now, at this other side, so you expect neutrons from here, yes? There is absorption because the diffusion equation has absorption. What is the absorption term? What is the absorption term in the diffusion equation? 1 over L squared. It is hidden here because L squared is square root of D over sigma absorption. So there is absorption. So there is absorption. If this is just a medium, you expect that you will have some 1 over e to the power of minus e something. Yes, e to the power of minus e whatever over x or x. You expect that you will have a decay or something like this. So because now you have a source that feed neutrons inside, the neutrons might absorb here, then you will have neutrons coming out from the other side, and this is J plus. J plus at x equal to A. So what is J minus at x equal to A? 0. You do not expect from neutrons coming from a vacuum to get into your system. Yes? So now, if you will do the calculations, you solve the equation with the boundary condition as with the source here. So of course, I have to add one more term to this equation to be able to solve it. Yes? What's this? The source term here. And this is at x equal to negative A. Yes? So you have particular integral coming from this source term. Yes? So when you solve this, you will notice that the flux of x is equal to Q naught sigma scattering e to the power of minus sigma scattering over A divided by D sigma square, I think total, minus 1 over L squared sinh 2A over L this multiplied by this functional form here, e to the power of sigma total A sinh A minus x over L plus e to the power of minus sigma total A sinh A plus x over L minus e to the power of minus sigma total x sinh 2A over L. Okay, guys, maybe we can give this in one of the problems, maybe homework problem, or try to solve it later to see how we will solve this type of problem. It's just how to solve differential equation. You have to understand what's the physics and how to solve the differential equation. So, first principle. I have a differential equation, you have to write the differential equation in the right form. You have to include the source term, you have to include this and that. You have to understand what are the boundary conditions, what are the source terms, what are the source conditions, and so on. And then you start solving the diffusion equation in the correct coordinate system. And this will be solved in x direction. So, let's move to another definition. So we knew that we have in nuclear engineering, this is just a aside, we knew that we have current and we have flux, beam, intensity, flux, current, and now we have Q. So those are pretty much all the fluxes and sources that you will see. So you have beam, it's one direction, one energy per centimeter square per second. Flux, all direction, it might be energy dependent or non-energy dependent per centimeter square per second. In one direction, it might be a function of energy or not. So this is not a function of energy, this is function of position and energy, and also omega. And this is, and maybe if you want to make it a little bit complicated, so it will be time. And omega is the direction. Of course, this is a scalar quantity, and this is a vector quantity. And this is R, E, omega, T. And this is per centimeter cube. So everything here is per centimeter square per second, here per centimeter cube per second. Now we will define what we call albedo boundary condition. Albedo boundary condition. So if you look at the problem that we just stated here, if you have a medium like this at x equal to 0 and at x equal to a, and you have some, let's say, neutron current that's getting into the surface. So this is Jn. What's Jn? Is J plus at 0. Yes? You expect that there is some scattering that will happen from the surface, and you will have J out. And what's J out? Is J minus at 0. So the albedo is alpha, and it is just equal to the outgoing current at the boundary divided by the ingoing current at the boundary. So if we look at our slab model, we knew that the J plus is just equal to phi at 0 divided by 4 from the first derivation that we did for the diffusion equation, and this is minus d over 2 d phi by dx at x equal to 0. So what's J plus? J plus is what? Is Gn. And J minus is just, it will be the plus sign here. So if you try to calculate the albedo, it will be just J minus over J plus, all evaluated at 0. And you will notice that this is from the flux shape in finite slab, for example. This will be just 1 minus 2d over L multiplied by the cotangent hyperbolic of A extrapolated divided by L, all divided by 1 plus 2d over L of the cotangent hyperbolic of A extrapolated over L. So what if A over L become very large? A over L is very large. That the thickness of the slab become very large compared to your diffusion length. So in this case, the cotangent hyperbolic of A plus lambda extrapolated over L will go to 1. The cotangent will go to 1. And in this case, your alpha will be just 1 minus 2d over L divided by 1 plus 2d over L. So it's better to wait to stop here today and then continue next time. So did you have any question regarding this stuff? Is there anything that you do not understand?
So
Yeah, go ahead.
that one is a slab medium, all in between.
It's a slab medium, yes. Slab medium, but you have only neutrons. You do not have any sources inside the
Right.
slab, but you have neutrons coming from the boundary, penetrating through the medium. And it asks you, okay, solve the equation, find the flux, find the albedo, for example, and so on. And the albedo is not defined inside the medium. Albedo is only defined at the interface, at the surface. So at the surface, you get the current out and current in. You divide those ratios, you get the albedo ratio. Yes.
My question was kind of like, what's the purpose of the albedo? Like, when you find it, what do you say after that?
In this course, specifically in this course, usually we'll ask you to calculate the albedo. The idea of calculating albedo in this course, it will be just to train you to be able to calculate what is the flux first inside the medium, then calculate the flux at the surface, then get the J minus and J plus from those two formulas, and then you will at the surface, and then divide them, you'll be able to get the albedo. So the albedo here, just in this course, it will tell you how to calculate the current, then the flux, and again get the ratios for the current minus. And so it builds in you how to calculate the basic properties of the medium, like what's the flux inside the medium, what's the flux at the surface, what's the current at the surface, the inward current and the outward current. You have to not memorize, you have to visualize those. But usually the albedo will have different usage in advanced courses. Maybe the albedo will get into one of the formulas of the advanced courses, for example. So when we will go on and continue the diffusion equation in multiplying medium, for example, we'll be solving the same, but now the medium is multiplying. Then we will solve what we call criticality equation, and this criticality equation will tell us what's the shape and size of a critical, let's say, a critical mass in a spherical geometry, for example, or what if our reactor is a parallel pipe, what should be the critical dimension, and we will transform from the diffusion equation to what we call critical equation. But this is in the next chapter or so. But this is, for right now, is to train you how to calculate the flux. Then once you knew the flux, calculate the flux at the surface. From the flux in the surface, you will calculate the currents in the surface, the inward and outward current, the minus and plus. Then the albedo will just give you the ratio, and you will be able with the albedo ratio to figure out, okay, this is the shape of the albedo at this. Okay? That's it. Any other question? Nothing? Okay. Have a wonderful time. See you next lecture.